So, for example, let's go back to this rather long sequence and apply the permutation test. See if it's possible, okay? Because it's simply I think it's too difficult to check the distance rule with every pair of integers and so on. All right, so what we do is we add 0 to this first, actually I'll use the pointer. We add 0 to the first number, 1 to 3, 2 to the next one, 3, and so on. Here we've worked out that p is equal to 12, right? So we've got a sequence 12 digits long, right? So I'm going to add each of these numbers together. So we end up with this, 2, 4, 7, 6, 12, and so on. And now what I do is take each of these resultant integers mod 12. Okay, so when I say mod 12, I mean if I get 12, then that's going to be 0. Right? If I get 13, that's going to be 1. So it's like the remainder that's left over when I divide through by 12. Okay, so what does that look like? Taking mod 12, well, it's 2, 4, 7, 6. Okay, that looks close, but do we actually have a permutation of 0 up to 11? Well, it turns out we don't, right? Because in this case, we have the number 4 occurring twice. All right, so by the permutation test, no. This original pattern is not possible. It's not able to be juggled. All right, that's using the permutation test. Okay, so this pattern is impossible. That's the conclusion that we can draw from that. All right, now in the previous example, so if we go back and have a look at that, see we've only got 2 4s, right? That's the only place where it fails. So what if I actually wanted to try and turn this into something that I can juggle, right? What do I have to do, right? I need to change something up here in order that I have a permutation of 0 up to 11 down here. But what do I need to do? Well, it turns out the only thing I need to change one of these 4s, right? If I can change one of these 4s, now what's the missing? There must be one missing. 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so there's no 9. So we're missing 9. So actually I need to turn one of these 4s into a 9. That way I will have a complete permutation of the integers 0 up to 11. And so if I want to turn one of these 4s into a 9, what do I have to do up here in order to change that? All right, well, I change one of those 4s to a 9. All I have to do is add 5 to one of the corresponding entries, and then it should be no problem. Right? So this was just going back to the original number. These were the two problems. This 3 and that 8. They were the two problems that gave me the 4 and the 4 in the first place. So all I have to do is add 5 to one of those and there's my problem solved. I've got a juggleable pattern. Or in other words, I've got a pattern that I can juggle. So if I turn that 3 into an 8, then that means by the permutation test, it should be okay. I should be able to juggle that. All right, well, when I say I should be able to juggle that, I mean in principle. Turns out I cannot juggle that, but maybe Joe can help me out here. There we go. Can you see that? So maybe a little bit hard to see. See these really high throws here? They would be the 8. They would be the 8th throw. Okay? Because remember, the size of the number represents the height of the throw, or is associated to the height of the throw. So this high one is the 8, and I can't remember what the other digits are, but you can see it actually looks quite complicated, and I would be very impressed if anyone could actually juggle that pattern. But certainly Joe here can show us a thing or two about juggling. So, okay, we've seen how we can adapt failed patterns. All right, how we can turn a pattern that isn't going to work into one that will. All right, now what about this asks the question, now that we've worked out how to do this, can we construct all possible patterns of a fixed length, right? And it turns out there is an algorithm to do that, right? So, well, I'll go through the details of the algorithm, okay? Maybe you can, well, try and get some idea of how this works when I go through it in a bit of detail. So just to demonstrate, let's have a look at all 3-ball patterns of length 3, right? Let's try and construct all 3-ball patterns of length 3. Now, the first thing we want to do is list all the permutations of 0, 1, and 2. All right, so this is an exhaustive list of all the permutations of 0, 1, and 2. Now, the reason we start with that is because, well, given any 3-ball pattern, according to the permutation test, what we have to do is add 0, 1, 2 to that string, and if it gives us a permutation of 0, 1, 2, then we know it can be juggled. So essentially, what we're doing here in this algorithm is working backwards through the permutation test. Okay, so we list all the permutations, and then one at a time, we take each of those permutations and subtract 0, 1, 2, right, from each permutation. Okay, so then we'll have a new list of numbers. The next step, we'll call those P prime in that list. Okay, we take each P prime in our new list and calculate, well, this number, 3 minus the average of P prime. Remember, the average, you just take the sum of the numbers, divide by the length. In this case, the length is 3. All right. So again, this is really just working backwards through the permutation test. Okay, because we know 0, 1, 2 is always going to be a juggleable pattern, right? These are all the possible permutations. We subtract 0, 1, 2, because remember in the permutation test we actually add 0, 1, 2, and what we want to try and do is generate all the possible juggling patterns of length 3. Okay, so we calculate this number, and then we determine all the strings Q that sum to this number T, okay, whatever this number T is. And then all the possible patterns are simply this P prime, this one up here from step 2, plus 3 times this Q. So that's maybe a little bit complicated, and I don't want to go into the proof of why this works. And here I've said it's true up to cyclic redundancy. And what I mean by that is, for example, the pattern 5, 1 is actually equivalent to the pattern 1, 5. Okay, so this last step, when we say up to cyclic redundancy, I mean we don't treat those as distinct patterns. Okay, well, let's look at an example. So we'll focus on the permutation 1, 2, 0 from step 1. Okay, so remember step 1 was just list all of the permutations of 0, 1, 2, and in this case I just want to show you how it works. So we'll have a close look at this guy, 1, 2, and 0. All right, so we take our P prime, 1, 2, 0, we subtract 0, 1, 2, so that just gives us 3 1s. Right, we now take the average, okay, the average of this, right, simply 1. So and we take 3 minus 1 is 2. And now, in step 4, we list all the strings whose entries add up to 2, right? And this is an exhaustive list. This is all the possibilities, right? And then in the final step, we take our P prime, that's this string of 1s, and we add 3 lots of each of these ones to generate this string. Okay, that's this guy here is to ensure that we have the right average, because remember the rule is we must the average of the numbers must be a whole number, and it must be the number of balls that we're juggling. Okay, so in this case we end up with these guys. Now if we remove the cyclically redundant terms, we just end up with 7, 1, 1 and 4, 4, 1.